Binomial radical expressions are objective. We want to add and subtract rational expressions. So, like I said, we kind of needed, in fact, we did need, if we're going to simplify these first, we needed to know how to multiply these first before we could get to the part where we can add and subtract radical expressions. Now, one of the things we already know about algebra is in algebra there's no fruit salad. And that's because you can't mix apples with bananas and bananas with cantaloupe in algebra. Algebra is a picky eater. If we have apples plus bananas plus cantaloupe, we're done. Got to be in 3 different parts on the plate. Don't even like it when they touch. That's algebra. Algebra is a picky eater. So, if we're going to add or subtract stuff, it has to be exactly the same. And that holds for radicals as well. They have to be exactly the same to put them in the same spot on the plate. So, like radicals, are radical expressions that have the same index and radicand. Index and radicand. We better think about what that means again. So, if you've got a root, this little box here, that's where index is. And this number that's in this position, that's the radicand. So if we want to put them together, that has to be exactly the same as what we want to put it together with. If it's not, then we can't. So index, radicand, exactly the same. So basically that means the entire radical has to be exactly the same. And that's absolutely true. It has to be. So the properties of algebra tell us we can only add 1 terms. That's the picky eater part. X's go with other X's. Y's go with other Y's. But you can't mix and match them. It doesn't work that way. Because when we add, they must be like terms. So down here it says, essential understanding is you can combine like radicals using properties of real numbers. If we have the square root of 2 plus 3 square roots of 2, you get 4 square roots of 2. How come? Because there's a little imaginary 1 out here. If there's a square root of 2, it means 1 square root of 2. So 1 square root of 2 plus 3 square root of 2 equals 4 square root of 2. It's like saying I have 1 cookie, and now I'm going to get 3 more cookies, and now I have 4 of them. Yeah, and our label for cookies is a square root of 2. There it is. If we have 1 cubed root of 7 minus 5 cubed roots of 7, that's going to be negative 4 cubed roots of 7. So again, a little imaginary 1 out in front. If we have the square root of 5xy plus 8 square roots of 5xy, well, now we have 9 of them. If we have a cubed root of 9x squared y minus 8 cubed roots of 9x squared y, well, 1 minus 8 would be negative 7 cubed roots of 9x squared y. First thing we're going to have to check, are the radicals exactly the same? If they're not, we can't do anything. Now, sometimes if the radicals are not the same, there's some simplifying we can do to make them the same. And in that case, we have to do that simplifying. So down here, it says, no big shocker, if your radicals are exactly the same, just add the 2 numbers out front. That's what we're doing. We're combining like terms. If your 2 radicals are the same, just subtract the 2 numbers out in front. They're like terms. Just combine them like we already know how to do. So combining radical expressions is different from adding them. The sum of any 2 real numbers is a real number. That's called closure, by the way. It's one of the properties that your geometry book, I don't know why they skip it, but in closure, what we learn is when you add 2 real numbers together, you get a real number. When you subtract 2 real numbers from each other, you get a real number. When you multiply 2 real numbers together, you get a real number, etc. So combining those radical expressions, the sum of any 2 real numbers is a real number. So we can add the square root of 2 and the square root of 3 because they are real numbers. But it's not simplifiable. With a calculator, we could tell somebody an approximation, hey, I'll punch in the square root of 2 plus the square root of 3 and tell them what it is. It's not 5. It's not the square root of 5. It's not going to work. So if we find the square root of 2 and we find the square root of 3 and we add those together, we'll get 3.146, while the square root of 5 is 2.236. It doesn't work that way. The radicals have to be exactly the same. But what if we take the square root of 3 plus 5 square roots of 3. Well, now we're saying we have one of them, and we're going to add 5 more, and we'll get 6 square roots of 3. Because they are like radicals, it will work. If we punched in the square root of 3, well, you know what? I'm going to prove it to you. Prove that this works. So the square root of 3, there it is, plus 5 square roots of 3. Gives me this. 6 times the square root of 3. Exact same thing. So it works if we combine like radicals, but that's the only way it's going to work. Only way it's going to work. So, you gotta be kidding me. That's it for the box? It is. I mean, the boxes tell us what we need to know to do the section. Now remember, what they left out was this. If we could simplify it and somehow manage to get the radicals to be the same, then that's part of our job too. So here's what I'm looking for as I see what is the simplified form of each expression. The first thing I look for is it already simplified? And the square root of 5x, nothing we can do with that. You know? It's just the square root of 5x. We can't simplify that any further. And then I notice, well, this one is a square root of 5x, and that one's a square root of 5x. Okay, we can do this problem. Those are like radicals. 3 minus 2 is 1. And normally I wouldn't write the 1 down, but I want you in your notes to be able to follow that and see, hey, there were 3 of them, we subtracted 2. Big shocker, we have 1 square root of 5x. There it is. That's all we had to do. Take a look at B. Are they in simplified form? Nothing else we can do to them, right? Can we add those two together? Why not? What's wrong with them? Different radicands. Yeah, they're not like radicals. They have different radicands. So what's the simplified form? You're seeing it right now. That's the simplified form. There's nothing else we can do with it. There's no way to simplify the square root of 7 because there are no perfect squares that are going to divide into it nicely, and certainly none that are going to get us a 5. You know, dividing 7 by 5 is not going to give us something nice. So it's done. Not like radicands. Has to have exactly the same radical. So you have to have the same index and the same radicand. All right, take a look at C. Simplified? Like radicals? Did they bait you for just a second? Did you look at it and go, yes, those are like radicals. They've got a 7, an x, and a y for the radicand. What's wrong? The index is not the same. This is done. Nothing else we can do. Done. Can't simplify. Index is different. So we're glued into the radicand, but we also have to be glued into the index, because if they're not exactly the same, we cannot put them together. Which gives us 3 lovely little problems for you. And I'll get you a candy partner so you can check and see how you're doing on those. So go ahead and go through. Got it, A, B, and C. Can't simplify. Why not? Yeah, index is different. The radicand, again, they're kind of baiting us. We look up there and we go, oh, it's got a 5 under it. You know, everything's good, but we also have to check the index. B, could you do that one?
Yeah.
And what'd you get?
7.
Sounds about right. C, could we do that one?
Yeah.
Okay, both have the fifth root of 3x squared, so what'd you get? So far, we haven't had to do any simplifying to get stuff to mesh. And that's because they always start us off with, you know, the most basic problems. But what we have to remember is they have to have the exact same radical, both index and radicand, or we can't add and subtract. So if we find ourselves looking at a problem and saying, wait a minute, I can't do that one, we maybe better check and see if we can simplify first and then do the problem. So down here, kind of an odd place for the word problem, we plop it right in the middle and make us think geometry. The G word. Geometry. So we've got this nice little stained glass here, and it says, in the stained glass window design, the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. Okay, so the side of the squares are 5. So this is 5 and this is 5, and we would need that in order to figure out what the perimeter is, right? Because these would all be the same. We could be done with this problem if you remember special right triangles from right now. Well, and we're going to do it the long way. We can do the Pythagorean theorem. We absolutely can.
You can do them ratios. Doesn't you have to be doing ratios?
Do it this way.
On the right triangles.
Oh, yeah, the
45
45
degree, 45 degree. 2 squares.
I can't remember the numbers.
Not even.
I heard it though. I heard some people remembering. And all from the song. And some of you didn't learn the song because your geometry teacher doesn't sing. But remember, 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in the triangle game. So, if you look at this.
I think we need a clap.
Yeah.
Oh,
Yeah.
If you notice these two sides are the same, then you'll know, hey, wait a minute, that has to be a 45, 45, 90 triangle, and all I need to do is multiply 5 by the square root of 2, and I will have that side. So, this song, all the way through college trade, that's all you need to know. All the way through college trade, if you have that song, you will. And I have extra copies.
Oh,
So-
that's fantastic.
So now, what we need to do is realize all of these are the same. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So 10 times 5 square roots of 2 is 50 square roots of 2. Now, like I said, if you can't remember the song, you can't remember the special relationship in the 45, 45, 90, you can get it there with the Pythagorean theorem. It's just going to take you a little longer, that's all. But you'll get it. You know, and that's what's important on the ACTs or the MCAs is that, you know, if you backup plan, you gotta have a backup plan in case you forget. So we've got 50 square roots of 2, and what I would check is, did they say they want this rounded to something? Because that's a perfect answer. You know, I'd like to leave my answer perfect. But find the perimeter of the window to the nearest tenth of an inch. So I'll put it up here. I know you don't have your calculators with you. So we would punch it in and find out that we have 70.7, and this was in inches. And we'd have it. So the special relationships, they do help us go faster with the math. And your got it for you and your partner is find the perimeter of the window if the side of each small square is now 6 inches instead. is, yeah, we use that same stained glass pattern. All we're doing is changing the 5 to a 6. And yeah, we probably better see what that one is too. So 84.9 inches. And then in B, it says, you forget the special right triangles. Is there a different way you could do this? Yeah, you could use the Pythagorean theorem. So you could a squared plus b squared plus a squared plus b squared equals c squared on that one. And you could get, and like I said, that it happens. It's planned for, it's the reason we teach a book and show you how to use the Pythagorean theorem and the special right triangles. But for today's objective, we want to focus on whether or not we can simplify these first, and then we can do our addition and subtraction. Because sometimes we're going to look at them and go, wait a minute, oh, those aren't the same, done. No, exactly. If we simplify them, then maybe we could put them together. I mean, that's the big key, and most of the problems will be that way, where we do have to do a little simplifying. So, problem 3 has us simplifying before adding or subtracting, because it says, what's the simplest form of the square root of 12 plus the square root of 75 minus the square root of 3? Can't do it. The radicands are different. And it's simplifiable. So here's the educated cheat. Take a look at the 3 of them that are up there right now. Which one of those is obviously already simplified, and tell your partner? Which one of these is simplified? So if we're going to be able to do this problem, they all have to say square root of 3 times something. That's our educated cheat. So we look at this and say, well, 12, if I'm going to have square root of 3, that's going to be square root of, oh yeah, that makes sense. Square root of 4 is 2, I can do that. And if the 75 is going to be the square root of 3, that'd have to be a 25, oh yeah, 25, perfect square. So we'll have 2 square roots of 3 plus 5 square roots of 3 minus 1 square root of 3. 2 plus 5 is 7. That's 7 minus 1 is 6. And we have it. So the educated cheat, like I said, is to find the smallest perfect square that you have there. And if it's simplified, that's what you're going to need, or you won't be able to do the problem. So now, that one for you. So hopefully you and your partner can make your way through this one. I'll turn the lights up so you can see a little bit. But make sure that that smallest one is not simplifiable as well, because your smallest might be something you could simplify first. You know what, let's take like a 5-second break where you can run and get your graphing calculators, because I see some people doing some long division and stuff. So if you need your graphing calculator, go ahead and grab it. Partners, I want you to check with your partner and make sure they didn't make one of the common mistakes with radicals, and that is not putting the index in their answer. That is a common mistake. Make sure you check with your partner and see if they have that index in there. All right, everybody's partner remembered? Little 3 in there? So how'd you split 250? What'd you use?
Is that a big one? That was a big one.
Cube root of? 125n, yep, 2. So then you go after the 2 with all the rest of them so that you have a nice number to go out in front of all these in an integer. So we've got 5 cubed roots of 2 plus 3 cubed roots of 2 minus 2 cubed roots of 2 for a grand total of how many, everybody?
6.
6 cubed roots of 2. So that simplifying first makes this a problem that we can do. I want you to 4, 3, 2, 1, 0 me on our objective of adding and subtracting.
Feeling good today.
I am feeling
Really
today.
good.
Feeling good? Alrighty, let me get you some problems. Thank your partner.
Thank you.
And yes, the song is up here. Don't poo-poo the song.
I want one of them sheets.
Yeah.
I'm gonna sing on the shower.
Studying the shower.
It's a catchy tune. 30, 60,
And now it's time for a little song.